Hi everyone. Welcome to the second lecture on the foundations of machine learning. Today we'll go over a derivation of a mathematical model for supervised learning. And I know this lecture can be slightly a little bit more complicated than the previous lecture, but I promise you that if you just think about it with intuition, it's not all of that difficult, right? So let's think about what supervised learning actually is. Last time we talked about this concept of a machine learning model as a function, right? Function meaning that if you have some sort of a input, let's suppose that it's f of x is equal to x squared. Let's suppose that we put in the number 10, then we're going to get 100 back, right? We thought about the concept of a machine learning as a function. So if you have something like all of your past songs or the past songs you've listened to, then we can predict the future song you might listen to. And the concepts in supervised learning model or supervised learning and unsupervised learning are somewhat similar, where in this case, we might have specific sets of features and and labels, and we're basically going to use that to generate some sort of a labeled output. Now, what do I mean by a labeled output? What do I even mean about features? And honestly, what do I even mean about a model, right? So let's leave the model aside. We'll basically see that in a little bit in a little bit later. But we can think about a very simple data frame or a data set, right? Last time we talked about capturing tabular data. Just because it was basically raining today, I'm going to get use this example of raining because I was unsure about how many students would come to lecture. But as a matter of fact, we had perfect attendance again. So that was awesome to see. In any case, let's hypothetically suppose that we want to be able to predict if it's going to rain or not, right? If it's going to rain, I'm going to just say, yes, it is going to rain. If it's not going to rain, I'm going to say no, yes, yes, no. And let's think about the different things that we can use to predict if it's going to rain or not. The temperature, the types of clouds, the number of clouds. There's a lot of things that we can use to basically predict if it's basically going to rain or not, right? So the temperature might be something, if the temperature is 20 and there might be nimbus clouds outside. I don't know if nimbus indicates rain, but I know that in Dragon Ball, there's this flying nimbus, right? There's this flying nimbus that Goku, uh, Goku rides, and in the flying nimbus that Goku rides, he's basically going from point A to point B, right? In the flying Nimbus that Goku is riding on, I imagine that it has to do something with rain. So I'm going to say flying Nimbus indicates that it's basically going to rain or not. And the number of clouds. Well, if there's more clouds outside, 100, then it probably indicates that there's a higher chance of rain, right? Or something better might be to take something like surface area, but we'll keep this model very simple, right? So we have 100 different types of clouds outside, or 100 clouds that are outside. And we can use that to predict if it's going to rain or not. You can see here that the outputs are labeled, meaning that we we basically tell the model if it's going to rain or not, and we indicate that with ones and zeros in this tabular data. Whereas in an unsupervised learning method, what would be different is instead, we would have no label. There would be no label. So we would just tell the model to figure out from scratch just by using these features. And by features, I mean the X values or the column names, the temperature, uh, types of clouds, just going to write types, the number of clouds, right? So those are the features. And then the Y value would be In supervised learning, it'd be rain or not. So in this case, there is no feature set that we give the data. So that's the difference between supervised and unsupervised learning. Remember, the goal of any function is to map an input to an output. And I think an easy demonstration of that would be the same exact example, right? So this model here is going to learn from all of this data. This model here is going to learn from all of this data in the case of supervised learning, and it's going to ask the question now, right? So this model is now very smart. Smart. So this model is now really, really smart. And now we're just going to say that right now the weather says that it's 50 degrees outside and there's a nimbus cloud because I don't know any other clouds. Uh, and there are two clouds outside, right? Is it going to rain or not? Maybe I could also pass in the wind speed, but the model has not been trained on wind speed, right? That's a question mark. Is it going to rain or not? So we want to predict the future, right? So it's sort of like this is like an somewhat like a astrologer, I guess, but but a more scientific astrologer, and it's going to give you some, some label back, right? It might say a one, right, with some probability. Let's not even think about probabilities right now, actually. It's going to say one or it's going to say zero. So this is a function in this case, right? It's going to map an input to an output, and you can also think about the same thing as what I told you about Spotify. So here are a couple of really, really strong and really difficult and challenging trick questions. Is this a cat, a dog, or neither? If you didn't laugh at that joke, you probably should have. And if you did, thanks for laughing. This is a cat. This is a dog. Maybe you guys laughed at this one. A lot of my students laughed at this photo for whatever reason. Now, is this a cat or a dog? I think it's neither. I do see a picture of me, and this is Mr. Atkins. So Mr. Atkins is a teacher at middle college. And I'd gone to middle college, and funny enough, he was actually calling Charles Schwab to take care of one of his one of the stocks that he was trying to trade, and we had a very funny laugh. So I based this entire lecture on Mr. Atkins, and I based this entire lecture on what Mr. Atkins was doing, which you'll see later. In any case, whenever you think about the world around you, it doesn't take much for us to delineate or separate if this is a cat, if this is a dog, if this is Mr. Atkins and Srijal. It doesn't take much for us to do that, right? However, with a computer, we have to train it. We can't just say, hey, this is a cat, this is a dog, and this is Mr. Atkins and Srijal. Like a computer has no idea what's going on when you say that. So what do? We encode the data set. So now we're going to say if it's a cat, it is equal to 100. If it's Mr. Atkins and Srijal, we're going to encode that as 001, right? And if it's a dog, we're going to encode that as simple. That is what I call encoding. And a lot of people get confused when they see this. R3. Y lives in R3 with this encoding. What this only means is just a dimension. This is the dimension. You can see there are three different dimensions, either indicating cat, dog, Mr. Atkins, and Srijal, right? Because a cat cannot be a dog. So this cannot be one, right? But you can see that this is just a three-dimensional input. And what's remarkable about the human eye is you can also even think about it as a function, right? Right now I'm looking at a Zoom screen, And what this Zoom screen is doing is it's assigning an input to an output. So as I'm looking at the Zoom screen, I see my lecture up and out, and it's saying that it's telling my brain that it's basically my lecture's going on, right? Or if I see a cat, then it's basically going to say, hey, it's a cat, right? That's what's remarkable. It's just because we're able to learn iteratively, or like we're able to see something, and even if we don't understand it immediately, we can glance at it, and we can kind of take time to figure it out, right? So it's sort of like this incredible unsupervised learning method where it's able to, even without labels, it's able to identify things and separate them into different categories, right? And whenever you think about the human eyes and even a computer, they're almost the exact same thing, right? Except I think like computers, they work in numbers, and the human's eyes, it might not necessarily be explicit numbers, but it does something similar, right? It assigns the input, in this case, the world around me, to an output. And this Y might be something super large. And with computers, it also does the same thing. It assigns an input X in an output Y. So the objective is to make the human eye similar, in this case, to a computer. Okay. So how do we make the human eye similar to a computer? We want to be able to penalize it every single time it gets something wrong, right? So for instance, let's take the same example back, right? Or let's take something slightly different, because that's more of a classification problem. Maybe we say something is a 70% chance of being a cat, 20% chance of being a laptop, only because I'm looking at my laptop and I have these nice sunglasses right here. So, 10% chance of being sunglasses. I know these are just random things that I just made up based on what I saw, right? So a computer looks at something and says, hey, there's a 70% chance of being a cat, 20% chance of being a laptop, and 10% chance of being sunglasses. However, the true label is a cat, or something like that, right? And we can use however, let's say the true label is a laptop. This would not be an ideal classification. Like, this would not be an ideal lo loss function for this specific category, but I'm still going to use this regardless because I think it conveys the intuition behind this. But what we can say is g of xi, remember, is what the computer, right, or what the computer assigned, right? In this case, it's basically going to predict a cat. So in this case, it predicts y hat denotes what it predicts minus the true value. Okay. So in this case, it predicts that it's a cat. So let's go ahead and fill in its y value is equal to cat minus, in this case, the true label is a laptop squared, right? And what's remarkable about a lot, or in this case, it's not a squared, but so I'm going to take it out. Uh, but in any case, what's remarkable is, we can encode this cat to being something like 0.7, um, whatever, right? And or it doesn't have to be 0.7, but that's what, like, this is kind of the penalty that you have to pay. In a classification, in all honesty, something like this is not even used, but I think it still conveys the intuition behind. I think it better conveys the intuition behind how models like this even work. Okay, so in this case, in iteration two, what I ended up doing was I ended up squaring it, right? So let's take the same example of a cat and a laptop. Before we said that it had 0.7 probability of being a cat, and the true value was actually a laptop with probability 1, right? And I want to give it some sort of a penalty for predicting, for predicting cat with probability 0.7. So I'm going to go ahead and say the penalty that you're going to earn is 0.7 minus 1 squared. So in this case, it's going to be 0.3 squared. That's the penalty that it earns. There's going to be a negative, but that negative is going to cancel. And in this case, the penalty it earned was a negative 0.3. But it doesn't make sense to give it a negative penalty. Therefore, I'm just going to go ahead and square it to kind of make it easier. And what's also incredible is that this function is very much differentiable, meaning that you can take the partial derivative of it, right? So more often than not, you'll see this as sort of like the convention. And if you're um, at all interested, then we can think about something in iteration three, where in this case, let's hypothetically imagine that we have y hat is equal to, let's suppose that this is a series of predictions. So cat, um, what else? Cat, uh, first I predict cat, then I predict cat again, then I predict sunglasses, right? But the actual values instead are, um, let's say the actual values, the first value that I said was actually a laptop. So we know that. Let's suppose that this is indeed a cat, and this is actually a laptop. So the penalty that this function is going to incur, this looks like a very tough function, but it's pretty easy, right? N basically indicates how many values we have altogether. In this case, we have three values, so that's simple. So 1 over 3, right? And summation just means that we have to add them all up. So as an example, cat minus laptop squared plus cat minus cat squared plus sunglasses minus laptop squared. Think about this as kind of probabilistically, right? Think about this as probabilistically. And what I mean by that is similar to how I transformed cat into a probabilistic approach. Think about doing this probabilistically, right? It's a cat with probability 1, and we did predict cat with probability 1. So 1 minus 1 is 0, so this is going to go to 0, right? And I know that in classification models, these sorts of loss functions are not necessarily used or always used, but I think it gives a better intuition for what we are gonna do, in future lectures. That's the only reason that I brought it up. Now let's go ahead and take a step back and think about what a line is. How can you mathematically represent a line? We have seen it since algebra. We have seen it in more than likely in middle school, but we have not always kind of paid attention to it, right? Y is equal to mx plus b. That same formula is something that we're going to use to derive our very first supervised learning method. So what I mean by that is this is a line. Let's go ahead to the next lecture or the next slide. This is a line. This is y is equal to x. This is x is equal to 1. You can see that for all values, x will always be 1. And in this case, for all values, y is always going to be 1, right? So therefore, this is a line. And lines always come with the form y is equal to mx plus b. In this case, instead of m, I'm going to use the word w. But just think about w as being the slope, and b, of course, is the intercept, right? Similar to what you think about in a traditional algebra class. So, inspired by the notorious traitor of middle college and the uh, Berkeley community or the larger San Pablo community, Mr. Atkins, I thought about why not use a example that is actually relevant um, to students like you. And Mr. Atkins, the famous trader, wants to know, here's a Nimbus cloud, but Goku's not going to write on this one, right? Mr. Atkins wants to know Is the stock gonna go up? And this is me, the machine learning model. Okay, I'll tell you soon. Okay, great. So I've just made a promise to Mr. Atkins that I'll tell him if the stock is gonna go up or not. And I have to fulfill that promise. That's why I'm gonna take Srijal's machine learning class to understand how I can predict if a stock is gonna go up or down, right? So think about it like this. Every time a stock goes up, I'm gonna give this machine learning model $1. Every time it goes down, I'm gonna take away $1, right? Maybe $1 is not the best way to think about it because it's a loss function, but you could kind of also interpret it like that if that kind of helps add to your intuition. And X is the set of features that we have. So yesterday's price, today's price, market's going up or not, the number of tweets that are there, and then all of that is going to be used to predict if the stock is going to go up or down. But wait, there's something wrong here. And there's also something wrong here too. But there's something wrong here even more, right? We notice that these values are not encoded. So why don't we go ahead and encode those values? If it's yes, then it's a 1. And if it's a no, then it's a 0. I'm just going to replace 1, 0, 1. Okay, great. So I went ahead and drew this specific example of a classification model where there is like well extended and well separated clusters. And in the x-axis, we have something like yesterday's price. What was the price of the stock yesterday that Mr. Atkins wants to trade? And how many tweets are there? Or like what exactly is the social media hype, right? Is there like a lot of tweets about this company? Is there too few tweets about this company, right? So these are the tweets. And here, depending on that, we can see that there's actually a relationship. The higher the price, the more tweets that there are about this company, the more likely it is that the stock's going to go up, right? And we can also discern another pattern. The lower the price, the lower the tweets, the less likely that a stock is going to go up. So let's go back to our data science, or yeah, like the data science framework of thinking about questions or thinking about these sorts of problems. We have a question at hand. Is the stock going to go up tomorrow? And we want to be able to answer this question, right? So what do? We acquire data. And we have already done this. This is definitely not enough data, but at the same time, I also have to give an example. So just suppose that there's only 3 rows. And then we have to do some data analysis or data visualization as I think it was, and then data analysis. I think that was Raman who correctly pointed that out the last time, right? That's great. And then based on the data analysis, we make some sort of a model slash prediction. And then we go ahead and deploy that model. Cool. So we have the question at hand. We have acquired the data. We have visualized the data. Let's suppose we have done some sort of data analysis on this. Now let's think about this model. How can we create this model? Do you guys see any sort of pattern in this data set? If you said I do, then I also do. Then that's the correct answer, basically, right? You see that, well, I already mentioned the pattern. The higher the price and the higher the tweets, the more likely the stock is going to go up tomorrow. So you can see that there's this pattern right here kind of bubbling out, right? There's this pattern that's bubbling out. And a couple of students, I think Aiden it was, today in lecture, pointed out that this is a way that this is one line that could basically be used to separate both of these companies. And then another student pointed out that this was is very specific. And he said that this is a pattern that can separate these two lines. Both of them are correct. And as it so happens, there are infinite variations of lines that could even separate this specific pattern. So how do we know which one is the correct one? And that is what our model is going to try to answer. Now, this slide looks somewhat scary, but let's go ahead and ignore this specific column for now. Let's go ahead and ignore that column. Great. So let's go ahead and ignore that column and let's just focus on two separate columns for now. What the price was yesterday, the number of tweets. I know that tweets can't be in fractions, but just hypothetically suppose that for whatever reason, in this case, it can be. So we see something pretty interesting, right? We can try to see if there is actually a linear relationship between yesterday's price, the tweets, and if the stock is going to go up tomorrow. I'm going to go ahead and round out these values. So 142 W1 plus 4.57. I should also round this out. So I'm just going to call it 5 W2 is equal to positive 1, right? Positive 1 meaning that it's correct. This should actually be greater than or equal to positive 1. Well, why, you might ask? It's because it's living above, right? It's living above. So I'm just going to call that positive 1, meaning that it's correct, right? And then in the case of the no, this 85 and 1, 85 W1 plus 1 W2 is less than or equal to negative 1, I think. Right? Yep. So it's less than or equal to negative 1. So this is the exact same thing that I did here, right? And the purpose of this model is to identify weights that make this equation correct, that make these equations also correct. Great. So what weights and intercepts can even make this possible? Let's think about it in the perspective of margins. This might not be the best line, but let's hypothetically suppose that we have these sets of two parallel lines. Parallel line 1, parallel line 2. So we have line 1 and we have line 2, right? I'm going to give you guys this one formula that you typically learn about in linear algebra, and I just hope that you guys just take it as an absolute truth. That is the distance between two parallel lines is given by line 1 minus line 2, the absolute value, all over the norm of these weights. When I do a WN, that just means that n is it's n units long, right? Or, better yet, just to make it even more conceptual, just suppose that there are only 10 weights in this model. So W10. So that's the distance between two parallel lines. Okay. Now we're going to go ahead and derive that equation. How? Remember, we have this great formula. You're going to go ahead and copy it. This is the very first line that we did identify, right? So I'm going to go ahead and move everything to the left side. Okay? And we're going to call this the very first line. And why don't we do the same exact thing for the second line too? Line 1, line 2. And if you guys don't believe me, you can also reference the past slide. Okay. Again, I'm going to move everything to the left-hand side. So we have these two lines now. Great. Distance between line 1 and line 2, therefore, is this is supposed to be a plus sign, right? Yep. Over the norm. In this case, we had 10 weight values. In this case, we only have 2 weight values, right? So we can just say W1 plus W2. Fantastic. Now we're on to something. Do you guys see something here? There are things that are very much repetitive. Minus W1 X1. I see that right there. Minus W2 X2. See that right here? That can be crossed out. B. Oh, wow. That can also be crossed out. And then what we're left with is minus 1 absolute value over square root of W1 plus W2. That's just going to give us the absolute value of negative 2 over W1 plus W2. We know that the absolute value of negative 2 is just 2. There you go. That is the final model. Now I'm going to give you guys another form of the norm. Whenever we do W1 plus W2, that indicates that it's the norm. Okay? So for instance, if I tell you what is the norm of let's suppose that the weight 1 is 8, and then you have the second weight is basically also 8. 8 plus 8 is 16, so that's equal to 4, right? So that is exactly what I mean by the norm. So in that case, now we have what do we want to maximize? Remember that we wanted to maximize the distance between these two lines. The distance between the two lines. However, we also have constraints. We must ensure that these values remain above and these values remain below, right? And this is what this equation does here. These values indicate that they're remaining above the line, and these values indicate that they're remaining below the line, right? So is there some way of writing that that's actually a little bit more formal? This equation right here. Now you guys are a little bit more confused, I imagine. What is this y doing out here, right? Y just indicates if we denoted that as a 1 or if we denoted that as a negative 1. So let's suppose that it got denoted as a positive value, indicating that the stock is going to go up. 1 W1 plus, supposed to be for all, 1 W1 plus 1 W1, oh sorry, X1, right? Plus W1 X2 or W2 X2, right? Plus B is equal to 1. So we can see that there's a 1 here, and that's just going to simplify to W1 x1 plus W2 x2 plus B is equal to 1. Now, on the other hand, if this was a negative value, then this negative would go on the other side, right? So if you look above, that's something that's basically very much similar to what we derived before, where there's a negative on this side. So it indicates that we want to be able to find values so that we want to find the weights so that these values are classified as negative ones and these values are classified as positive ones. And we have derived the math to our very first machine learning model. And that's great because that really is what you end up doing with a machine learning model, or that's really how you end up thinking about just about almost every machine learning model that exists. You try to think about what the intuition is, which we did. We try to think about what the question is, the intuition is, the data basically looks like, and using that data, we want to be able to map that to some sort of a model, which we did, right? We're talking about this very simple concepts of lines, and really, I haven't really done anything complicated in any of these slides, and we're able to derive something that could be of use. And what typically ends up happening is there is a optimization technique that you can use to solve for these W's, but it's just more math, right? Which I unfortunately in this course don't have the time to go over. But if you want more time, this is supposed to be a plus minus, but anyways. Um, we just use it as a plus for, right? So in any case, yeah, you can kind of read more about this optimization technique that's on the internet. But this is just called support vector machines in case you guys are curious. See if there is anything else. We talked about this model. Now we have also done the model, and now it's time to deploy this model, meaning that we gather a bunch of data that maybe actually looks real, and we use this data to be able to make some sort of a prediction on if the stock that Mr. Atkins is trading is going to go up or not. And now I can go back to this Nimbus cloud and I can say, I have an answer for you, Mr. Atkins. You're going to lose money. Mrs. Atkins more than likely is not going to be happy with that. So maybe Mr. Atkins shouldn't have been investing money in Charles Schwab.